The video for this standard is solving exponential equations. Our objectives include solve with exponential equations with equivalent bases, solve with exponential equations with different bases, and then solve exponential equations quadratic in form. We start with working with equivalent bases, and a note, the one-to-one, might remember a 1-1. Notation for that, property of exponential functions states that for any real numbers b, m, and n, where b is greater than 0 and b not equal to 1, we have that b to the m equals b to the n if and only if m equals n. The if and only if just means that works in both directions. So if we have a number m equal to n, we can raise them to the same base, so b to the m would equal b to the n. We're going to use it the other direction a lot in this class, the forward direction, the way we wrote it. If we have b to the m equals b to the n, namely saying we have the same base on both sides, it means we have the same number of factors of the base on both sides. So that's all that exponent tells us, and we'll use that to solve. So for the first one, we could do it two different ways, but if you remember that 81 is just 9 squared, we can use that to rewrite with the same base. So we have 9 to the 3x minus 5 equals 9 squared is how we'll rewrite 81 to the x plus 4. Then we're using all of our exponent rules along with some log rules in these next two sections to break them down. So we'll do one more step. Write it as 9 to the 3x minus 5 equals 9 to the 2x plus 8 as we multiply those exponents together when we raise to another power. And now we can see we have the same base on both sides, right? Base 9, so we can go ahead and set those exponents equal to each other. The fact that these expressions are equal mean 3x minus 5 and 2x plus 8 have to be equal because they are the exponents that tell us how many factors of 9 we have on both sides. And for these expressions to be equal, we have to have the same number of 9s. So we can do that. We can subtract our 2x on both sides, add our 5 on both sides, and 3x minus 2x gets us our solve for x. 8 plus 5 gives us a 13. If you did want to go to 3, if you saw that, or really a lot of times it'll say go to like the lowest base, so we can hopefully not make a mistake as we go down, but we can write 9 as 3 squared to the 3x minus 5 would equal 81 would be 3 to the 4th to the x plus 4, and then we'd end up with 3 to the 6x minus 10 equals 3 to the 4x plus 16. Again, we have the same base on both sides, just base to a power. So we can set those exponents equal to each other. Our 6x minus 10 equals 4x plus 16. We can subtract our 4x on both sides, add our 10 to both sides to get all the constants away from the x we're solving for. We end up with a 2x equals 26, and then if we divide out that that 2 to solve for x, we end up with x equals 13. So either way you see it is fine. A lot of books, or if you look things up, they'll ask you to go to the lowest possible base they have in common. For b, we have 4 to the x, and a 0.25, which we can rewrite as 1/4. But of course, 1/4, we can use our exponent rules to rewrite it as 4 to the minus 1st by bringing that 4 up to the numerator. And from there, we have the same base, so no reason to go down to a 2 or something. But we'd get that x is equal to -1. All right, a little more work for c. We're starting with 27 to the x plus 1 equals 1/9 to the x minus 3. 27, you might remember, or can try a little trial and error, is 3 cubed, so 3 to the 3rd to the x plus 1 equals, we could do it in steps if you want, or we could do a little scratch to figure it out. 1/9 is the same as 1/3 squared, which would be the same as 3 to the minus 2nd, that same rule we just used for b. So we can write the right side as 3 to the minus 2nd, all raised to the x minus 3. Then we can do our multiplication. We have 3 to the 3x plus 3 is equivalent to 3 to the minus 2x plus 6 as we distribute that -2 through. You can do that as a second step if you want. But either way, we're going to get to the same base 3 equal to two different values. We're going to take those expressions from the exponent, 3x plus 3 on the left, and set it equal to minus 2x plus 6, our exponent on the right. We can add the 2x We get all our x's on one side, subtract our 3 from both sides at the same time. We end up with a 5x equals 3. And if we divide out that 5 to solve for x, we end up with x equals 3/5 here. For d, we've got base 5 on the left and 25 so far on the right. So left side is already prime, that base. We can write it as 5 to the x squared minus 3 still. For the right side, the 25 we'll write as 5 squared to the x, which gives us 5 to the x squared minus 3 equals 5 to the 2x. And then we can set our exponents equal to each other. X squared minus 3 will be equal to 2x. We see that square, so we have a quadratic. We want to bring the 2x over to the left side to get this equal to 0. So we can factor and use that zero product property to solve. So x squared minus 2x minus 3 equals 0. The only way to factor 3 is with 3 and 1. We want a negative 3 and a positive 1 to give us that negative 2 left over. And then we can write it out if we need to. If not, you're welcome to just write the answer, but I'll do 1 here. X plus 1 equals 0, or x minus 3 equals 0. So x equals negative 1 or 3. You can always sub back in and check. And the nice thing about working with equations, if we substitute those values in for x, we can make sure they actually work. You might need a calculator for some of the bigger ones, but hopefully you can trust yourself. As we move to solving with different bases, we need a property for logs. So we have the same thing. I'll write it out. The 1-to-1 property of logarithmic functions states that for any real numbers b greater than 0, m greater than 0, and n greater than 0, where b is not equal to 1, we get that log base b of m equals log base b of n if and only if m equals n. Again, it's an if and only if statement that's going to work in both directions, and we will use it in both directions. But for now, we're going to start with 2, solve the following exponential equations. We have 5 to the 2x minus 3 equals 8 to the x plus 1. We can factor 8 to get some 2's, but there's no way we can make it equivalent to 5, which is prime. So we have to use a log rule to bring those down, namely this 1-to-1 property of logs, and then our power property for logs. So in this section, we're starting with the m equals n, two equal expressions. We're going to bring in that log on both sides. You can use whatever base you want, but in general, it's going to be easier to write ln, so we'll use that a lot unless we need a different base to solve. When working with log equations, we'll start on the left and work to the right to say that those arguments are equal. But we start here with ln on both sides. So ln of 5 to the 2x minus 3 is equivalent to ln of 8 to the x plus 1. We can use our power property for those logs to bring the 2x minus 3 out front on the left and the x plus 1 out front on the right. Because there are multiple terms, we need to use parentheses. So it's a 2x minus 3 times the natural log of 5 would be equal to a quantity x plus 1 times the natural log of 8. We have x's on both sides, and we're trying to solve for x, so we need to distribute. You can write it out a couple different ways, but I'll do a 2 ln 5 times x, so we see the 2 ln 5 is like our coefficient on the x term, minus 3 ln 5 is equivalent to ln of 8 times x plus ln of 8. There are other rules for logs you could use here if we bring that 2 up as a power, or we bring some logs together once we get all the logs without x on the same side. But in general, for your exact answer, you don't need to simplify it all. You would end up tossing whatever you get into a calculator. Doing more steps leads to more possible mistakes. So our goal is not to simplify the logs or do anything. Our goal is to solve for x. So I'm going to move this natural log of 8x to the left by subtracting. And I'll move the 3 ln 5 to the right by adding it to both sides. So I end up with a 2 ln of 5x minus ln of 8x equivalent to our natural log of 8 plus 3 natural log of 5. On the left side, I have 2 terms with an x as a factor, so I can factor out the x. So x times our quantity, 2 ln 5 minus ln 8, is equal to ln 8 plus 3 ln 5. And to solve for x then, we just want to divide out that whole factor that's being multiplied by. So x would be equal to ln of 8 plus 3 ln of 5 divided by 2 ln 5 minus ln 8. And that is perfectly fine for our exact answer. For b, we've got a base of e on both sides. We can see e to the 4x times e to the x minus 1 on the left. So we want to use our exponent rules to add those exponents when we're multiplying the same base. So e to the 4x plus our quantity x minus 1 is equal to 5e. We end up with an e to the 5x minus 1 equals 5e. We want to divide that e on the right side out of both sides to get all of our e's together. That has power 1, or exponent 1 right now. When we divide with the same base, we subtract the exponents. So e to the 5x minus 1 minus that 1 from the denominator is going to be equal to 5. And we end up simplifying. We get e to the 5x minus 2 equals 5. We remember, hopefully, that ln is log base e. So when we do use ln on both sides here, natural log of e to the 5x minus 2 equals natural log of 5. It's going to simplify that left-hand side to just 5x minus 2, right? We'd bring it down with our power rule anyways out front, but the natural log of e is just 1, right? So maybe a little recall, scratch something over here. Natural log of e equals 1, because really natural log of e is log base e. And log base e of e would equal 1 because we'd convert to exponential, get e to the first equals e. All right, so on our left side, we just have a 5x minus 2 equal to natural log of 5. We can add our 2 to both sides. Maybe we don't have to write both of these steps, but 5x equals 2 plus ln of 5. And then we divide by 5. I'll do it without writing so I can finish it here. 2 ln 5 over 5 would equal x there. All right, a couple more. Solving equations, quadratic in form now. 3, solve the following exponential equations. For a, we have e to the 2x minus 6e to the x plus 5 equals 0. That e to the 2x, if we're multiplying in the exponent, we know we could rewrite it as e to the x to the second power. When we raise to a power, we'd multiply those exponents together to get to the 2x. But we want to view it as something squared. Minus 6e to the x plus 5 equals 0. That's our quadratic in form. If you want to, you can do the u equals e to the x, and u squared equals e to the x squared. Or just know that e to the x is standing in place for your x, and we can factor with an e to the x as our first term in both of our binomials. We need factors of 5 that give us negative 6, so both are going to have the same sign because of that plus 5. We want minus 1 and minus 5. Our zero product property then says e to the x minus 1 equals 0, or e to the x minus 5 equals 0, which would give us that e to the x equals 1, or e to the x equals 5. For the left one, e to the x equals 1, we know our power has to be 0 there. Anything or any number to the 0 power gives us 1, so x would be 0. For the right side, we can use that natural log 1-to-1 property to say our natural log of e to the x equals the natural log of 5. The left-hand side would again just go to that exponent x, and the right-hand side would stay natural log of 5. So we've got 2 answers there for our quadratic. For b, we have e to the x plus e to the 3e to the minus x minus 4 equals 0. You can rewrite it first if you want to see where that e to the minus x is, right? It goes in the base of its term with that exponent rule for the negative power there. And then we can multiply both sides by e to the x. To get rid of those denominators, we end up with an e to the x times itself, or an e to the x squared, plus 3, right? As we distribute into the second term, that e to the x that we're distributing in is going to divide out with the factor in the denominator. And then we'll get a minus 4 e to the x, all equal to 0. So we can rewrite it. So we have it in our quadratic descending form, the e to the x squared minus 4 e to the x plus 3 equals 0. For our factorization, again, that e to the x squared would give us an e to the x in both binomials. We have a positive 3, factors of which we need to make a negative 4, so we get a negative 1 and negative 3. Our zero product property gives us that e to the x minus 1 equals 0, or e to the x minus 3 equals 0, which means, again, e to the x could equal 1, or e to the x would equal 3. For the left one, we know x would be 0. For the right one, we can use that log again. Natural log of e to the x equals natural log of 3, so x would be our natural log of 3. And for c, we've got a different base now. We've got 5 to the 2x plus 3 times 5 to the x equals 28. We can rewrite that first term as 5 to the x squared. So still a exponential, right? 5 to the x plus 3 times 5 to the x. So our coefficient 3 there. And then we can subtract the 28 over to set this equal to 0 and get it in that quadratic form. Our factorization, we want factors of negative 28 that give us a positive 3. So the 5 to the x is going to be our first term in both. And then we want a positive 7 and a negative 4 to multiply to the negative 28 and add to 3. That'll give us two options with our zero product property. 5 to the x plus 7 equals 0, or 5 to the x minus 4 equals 0. For the left one, we'd get 5 to the x equals negative 7. If you remember your range for those exponentials, we had to be from 0 to infinity. Minus 7 is not in that range. So we get no answer here, or no solution for this little mini equation. Right, think again, if I raise 5 to a power, if it's a positive power, it's going to be a bigger value, right? 5 squared, 5 cubed, 5 to the 4th. If I have a negative value for x, it's just going to push that 5 to the denominator, so I'd get 1/5, 1/25, 1/125, and keep getting smaller and smaller and smaller, approaching but never hitting 0. For the right side, I get a 5 to the x equals 4, and I can use ln if I want, or we could just use log base 5. I'll kind of show you both. It ends up being the same thing. But if we match our bases, so log base 5 of 5 to the x, we'd be equal to log base 5 of 4. On the left side, you could bring that x out front, and then log base 5 of 5 would equal 1, or you can remember that log base 5 of 5 to the x is just x. It was one of our properties for the logs. Would equal log base 5 of 4. But this, if you were going to throw it in a calculator, you can look up a change of base formula, but you either use ln or just common log base 10, because those are the ones on the calculator. We'd evaluate it by taking natural log of 4, that argument, over the natural log of 5, the base. And that's the same thing we'd get if we used ln from the beginning. Ln of 5 to the x equals ln of 4. We bring that x down as a factor, times ln 5 equal to ln 4, and then divide out the natural log of 5 to solve for x. So you're welcome to do it either way. We're going to hopefully be putting those exact answers on paper and into the homework. But try some stuff, come with questions.